Tonight, we're going to answer a question that sounds like it should be simple. How long does it actually take to reach each planet in our solar system? You'd think the answer is straightforward. Look up the distance, do some math, done. But here's what almost nobody realizes. Mars is not always the nearest planet to Earth. Mercury, one of the closest planets to us, can take longer to reach than Jupiter, a world nearly 500 million miles away. The fastest route to any planet is almost never a straight line. The real answer involves moving targets, curved paths through space, and launch windows that open and close like clockwork. By the end of this, you'll understand why getting to another planet is far stranger than you ever imagined. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let me start with the most common misconception about traveling to another planet. Most people assume it is basically about distance. You look up how far the planet is, figure out how fast your rocket goes, and divide. Time equals distance divided by speed. Simple arithmetic. It works for road trips, it works for airline flights, it works for virtually any journey you can imagine here on Earth. But it does not work in space, not even close. And the reason it fails is something that sounds obvious the moment you hear it, yet it changes absolutely everything about how interplanetary travel works. The planets are not sitting still. Every single planet in our solar system is in constant motion, orbiting the sun at tremendous speed along its own curved path. Earth itself moves around the sun at about 30 kilometers per second. That is roughly 67,000 miles per hour. You do not feel this motion because everything around you, the atmosphere, the ground beneath your feet, the oceans, the mountains, the entire planet is moving together at the same speed. But relative to the sun, right now as you listen to these words, you're hurtling through space faster than any bullet ever fired from any weapon in human history. And every other planet is doing the same thing. At different speeds, along different orbits, at different distances from the sun. Mercury races around the sun at about 48 kilometers per second. Venus moves at roughly 35. Mars travels at about 24. Jupiter, far more distant and tracing a much larger orbital path, lumbers along at roughly 13 kilometers per second. Neptune, out at the outer edge of the planetary system, crawls at just over 5. Each planet follows its own orbit at its own pace, and none of them ever pauses. Not for a moment. Not for a single second. The entire solar system is a vast clockwork of moving worlds, and every piece is in constant, relentless motion. This creates a situation that has no parallel in everyday life. The distance between Earth and any other planet is constantly changing. It shifts every day, every hour, every minute, as both worlds trace their separate paths around the sun. It is never fixed. There is no single number you can look up and call the distance to Mars or the distance to Jupiter, because that distance depends entirely on where both planets happen to be in their orbits at the moment you check. Take Mars as an example. When Earth and Mars happen to be on the same side of the sun, lined up in roughly the same direction, Mars can be as close as about 55 million kilometers. But when the two planets are on opposite sides of the sun, with the entire width of their orbits separating them, that distance swells to roughly 400 million kilometers. Mars can be more than 7 times farther away at its most distant than at its nearest. If someone asks you how far it is to Mars, the honest answer is that it depends completely on when you ask the question. The distance to Mars right now is different from what it was 6 months ago, and different from what it will be 6 months from now. This same pattern holds for every planet. Venus, the planet that makes the closest approach to Earth of any world in the solar system, can be as near as roughly 38 million kilometers when it passes between Earth and the Sun. But when Venus is on the far side of the Sun, directly behind it from our perspective, that distance stretches to about 260 million kilometers, nearly 7 times farther. And here is a fact that surprises nearly everyone who encounters it. Even though Venus makes the closest approach of any planet to Earth, on average over time, Mercury is actually our nearest planetary neighbor. This was confirmed by a careful mathematical analysis published in 2019. Mercury hugs the Sun so closely on its tight inner orbit that it never wanders far from any planet in absolute terms. Venus and Mars, by contrast, swing to the opposite side of the solar system and spend long periods at enormous distances from us. When you average the distances over years and decades, Mercury spends more time closer to Earth than any other planet does. The idea that Mars or Venus is always our nearest neighbor is simply wrong. The solar system is more complicated than that. This brings us to one of the most important challenges in reaching another world. You cannot aim at where a planet is right now. By the time your spacecraft crosses the intervening millions or hundreds of millions of kilometers, the target planet will have traveled an enormous distance along its orbit. It will not be where it was when you launched. If you aimed a spacecraft directly at where Mars sits in the sky tonight and launched at full speed, by the time the spacecraft arrived at that point in space, Mars would have moved tens of millions of kilometers farther along its orbital path. Your spacecraft would arrive at the place where Mars used to be, and Mars would be somewhere else entirely. Imagine throwing a ball at someone running across a field. If you throw directly at where they are the moment you release the ball, you will miss. By the time the ball arrives, the person has moved. You have to throw where they're going to be, not where they are. In space, this problem is vastly more complex because both the thrower and the runner are moving along curved paths at different speeds, and the ball itself, the spacecraft, does not travel in a straight line either. It follows a curved trajectory shaped by the gravity of the Sun. Now, here is where things become truly counterintuitive, where the physics of space travel diverges completely from everything your everyday experience has taught you. When a spacecraft launches from Earth, it does not start from rest. It does not begin at 0 speed, floating in some stationary void. Everything on Earth is already moving around the Sun at about 30 kilometers per second. The rocket, the launch pad, the engineers in mission control, all of it shares Earth's orbital velocity. When a spacecraft lifts off and escapes Earth's gravitational pull, it does not shed that speed. It carries Earth's velocity with it into interplanetary space. The instant it leaves Earth's gravitational influence, it becomes an independent object orbiting the Sun, starting with roughly Earth's orbital speed and Earth's position in the solar system. This is a point that even many space enthusiasts miss. A spacecraft in interplanetary space is not flying through a void the way an airplane flies through air. It is orbiting the Sun, governed by the same physical laws that govern the motion of the planets themselves. These are the same laws that Johannes Kepler worked out more than 400 years ago, and that Isaac Newton explained through his theory of universal gravitation. The spacecraft is on its own solar orbit, And the central challenge of reaching another planet is not about flying toward it in a straight line. It is about changing that orbit. The spacecraft must transition from an orbit that matches Earth's to a new orbit that intersects the path of the destination planet at exactly the right place and exactly the right time. To reach a planet that orbits farther from the Sun than Earth does, the spacecraft needs to speed up relative to its current orbit. Add velocity in the direction you are already moving, and your orbit expands, swinging you outward toward the outer planets. To reach a planet closer to the Sun, the spacecraft must slow down, shed velocity, and your orbit shrinks, allowing you to fall inward toward the Sun. But orbital mechanics contains a paradox that baffles nearly everyone who encounters it for the first time. When you speed up in your orbit, you move to a higher orbit, one farther from the Sun. But in that higher orbit, you actually travel more slowly overall. And when you slow down, you drop to a lower orbit closer to the Sun, where you end up moving faster. This sounds impossible, but it is a direct consequence of how gravity and orbital motion interact. An object in a lower orbit moves faster because it sits deeper in the Sun's gravitational well. An object in a higher orbit moves slower because the Sun's pull is weaker at greater distances. So, a spacecraft heading toward Mercury must shed speed to fall inward. Yet when it arrives at Mercury's orbital distance, it finds itself moving faster than it was near Earth, because it has dropped closer to the Sun. And Mercury itself orbits even faster still. Matching the planet's speed to enter orbit requires yet another adjustment, yet another engine burn, yet more fuel. This counterintuitive relationship between speed, altitude, and orbital energy lies at the heart of why interplanetary travel is so much harder than most people imagine. The most elegant solution to the problem of traveling between two planetary orbits is something called a Hohmann transfer orbit, named after the German engineer Walter Hohmann, who described it in 1925. The concept is beautifully simple. You fire your engines once at the starting orbit to enter an elliptical path. This ellipse stretches from your current distance from the Sun to the distance of your target planet. You then coast along that ellipse, engines off, letting gravity do all the work, expending no fuel during the long middle portion of the journey. When you finally reach the destination orbit, you fire your engines a second time, either to speed up and settle into the planet's orbit, or to slow down and allow the planet's gravity to capture you. Think of it this way. Imagine two circular racetracks, one inside the other. Earth runs on one track, the destination planet runs on the other. The Hohmann transfer is an oval-shaped path that just barely touches both tracks. You leave one track at a precise moment, coast along the oval, and arrive at the other track exactly where the planet happens to be waiting. But that last detail is critical. The planet has to actually be there when you arrive, and it will only be there if you launch at exactly the right time. This is why launch windows exist. A launch window is a specific period, typically lasting a few weeks, when the geometry of Earth and the target planet allows an energy-efficient transfer. The two planets must be arranged so that when the spacecraft arrives at the destination orbit, after months or years of coasting, the planet is actually there to be encountered. If the planets are in the wrong positions, no reasonable trajectory connects them efficiently, and the mission simply cannot fly. For Mars, a favorable launch window opens roughly every 26 months. That is how long it takes for Earth and Mars to return to the correct relative positions in their orbits. Astronomers call this interval the synodic period, the time between successive alignments of two orbiting bodies as viewed from the Sun. Miss the Mars window and your mission waits more than 2 years for the next opportunity. This is not a scheduling preference chosen by mission planners. It is dictated by the physics of two worlds circling the same star at different speeds on orbits of different sizes. Venus launch windows recur roughly every 19 months. Jupiter windows arrive approximately every 13 months. Even Mercury, which orbits so fast that it laps Earth regularly, has its own pattern of favourable alignments. These windows are the heartbeat of interplanetary exploration. Every mission to another planet is timed to one of them. Decades of planning, billions of dollars, years of engineering and testing, all of it converges on a launch date that is ultimately set not by human preference, but by the motion of worlds. Now, a Hohmann transfer orbit is the minimum energy option. It uses the least possible fuel to travel between two orbits, which is critically important because every kilogram of fuel a spacecraft carries is a kilogram that had to be lifted off Earth's surface against gravity. And lifting mass into orbit remains staggeringly expensive. Even the most cost-efficient rockets of the mid-2020s charge thousands of dollars per kilogram to reach low Earth orbit. And an interplanetary mission must go far beyond that. Fuel efficiency is not a luxury in space mission design. It is a survival requirement for the mission's budget and its engineering. But minimum energy comes at a cost in time. A Hohmann transfer is slow. A minimum energy transfer from Earth to Mars takes roughly 8.5 months. To Jupiter, nearly 3 years. To Saturn, about 6 years. To Neptune, the most distant planet, over 30 years. These are long, patient voyages through the silent emptiness of interplanetary space, with nothing to see and nothing to do but coast. So engineers have naturally asked the obvious question: can we go faster? The answer is yes, but the relationship between speed and fuel consumption is not gentle. It is not like driving a car, where going twice as fast uses somewhat more gasoline. In orbital mechanics, shaving even a few weeks off a journey can require dramatically more fuel. Engineers measure this in terms of delta V, the total change in velocity a spacecraft needs over the course of its mission. A faster trajectory demands a higher delta V, which means more fuel, which means a heavier spacecraft at launch, which means a larger and more powerful rocket, which means even more fuel to lift that bigger rocket off the ground. The problem compounds on itself ruthlessly. This compounding follows what engineers call the C-Olkowski rocket equation, and the relationship is exponential. Every additional kilometer per second of delta V requires not just a little more fuel, but a lot more, because you also need fuel to accelerate the extra fuel. The result is a practical ceiling on how fast chemical rockets can make an interplanetary journey. You can go somewhat faster than a Hohmann transfer by accepting a larger fuel budget, and many real missions do exactly this. But you cannot go dramatically faster without a fundamentally different type of propulsion entirely. The math simply will not cooperate. This is why there is no single answer to the question of how long it takes to reach a given planet. The travel time depends on the trajectory, and the trajectory depends on how much energy the mission can afford, which depends on the rocket, the spacecraft mass, the launch window, and the specific mission objectives. A minimum energy Hohmann path to Mars takes about 8.5 months. Some real missions have arrived in as little as 7 months by using slightly more fuel on a somewhat faster trajectory. In theory, with essentially unlimited energy, you could reach Mars in a matter of weeks, but the fuel required would make the spacecraft absurdly massive. Real missions live in the compromise between speed, fuel, and science goals. No two missions to the same planet take exactly the same amount of time, because no two missions fly exactly the same path during exactly the same orbital alignment. There is another factor that profoundly affects travel time, one that most people outside the space community rarely consider. What you plan to do when you arrive at a planet matters just as much as how you get there. Are you flying past it, entering orbit around it, or landing on its surface? These are three fundamentally different achievements, and each changes the mission in ways that alter the journey itself. A flyby is the simplest option. You aim your spacecraft so that its orbit carries it close to the planet. It sweeps past at tremendous speed, sometimes tens of thousands of kilometers per hour, relative to the planet's surface, collects data during the brief encounter, and then continues on its way deeper into space. The spacecraft never slows down. It never stops. It might get a few hours, or at most a few days of close-range observation, a fast snapshot of the planet's atmosphere, surface, and moons, and then the planet falls behind, and the spacecraft moves on. Flybys are the fastest type of mission because the spacecraft spends no fuel on braking. It arrives as fast as its trajectory allows and keeps going. Entering orbit is an entirely different challenge. To orbit a planet, the spacecraft must slow down enough to be captured by the planet's gravity. If it arrives too fast, the planet's gravity will curve its trajectory, bending its path, but the spacecraft will simply swing past and escape back into interplanetary space, never to return. To be captured, the spacecraft must fire its engines against its direction of travel in what engineers call an orbital insertion burn. This burn sheds enough speed to allow the planet's gravity to trap the spacecraft in a closed orbit. The amount of fuel required for this single maneuver can be enormous. For some missions, the fuel needed to break into orbit at the destination is comparable to the fuel used for the entire outbound journey from Earth. And if the engine fails during this critical burn, the spacecraft sails past the planet and into the void with no second chance. Because entering orbit demands so much fuel, mission designers sometimes deliberately choose slower trajectories that arrive at lower relative speeds. A spacecraft that coasts along a longer, more indirect path to a distant planet might take several more years to get there, but it arrives moving more slowly relative to the planet, which means the orbital insertion burn requires less fuel, which means the spacecraft can carry less fuel, which means it can dedicate more of its mass to scientific instruments. The trade-off between travel time and fuel cost shows up everywhere in mission design, constantly shaping decisions about trajectory, duration, and what the spacecraft can actually do when it arrives. Landing adds yet another layer of complexity on top of orbit. Once a spacecraft is circling a planet, it still has to descend to the surface. For planets with atmospheres like Mars or Venus, the atmosphere itself can help slow the vehicle. This process, called aerobraking, converts the spacecraft's kinetic energy into heat through atmospheric friction. It saves enormous amounts of fuel that would otherwise be needed for a fully powered descent. But it is also dangerous. The spacecraft must hit the atmosphere at precisely the right angle. Too steep and the heat becomes overwhelming, destroying the vehicle. Too shallow and the spacecraft skips off the upper atmosphere like a stone off water, bouncing back into space. Mars is especially challenging because its atmosphere is thick enough to generate dangerous heating during entry, yet too thin to slow a heavy spacecraft all the way to a safe landing speed. Engineers at NASA have described landing on Mars as 7 minutes of terror, and the name is well earned. For planets without significant atmospheres, like Mercury, there is no air to help. A spacecraft attempting to land there would need to use rockets alone for the entire descent, demanding large amounts of fuel and adding substantial weight to the mission. For the gas giants and ice giants, Jupiter, Saturn, Uranus, and Neptune, landing in any traditional sense is impossible. There is no solid surface to land on. A probe entering Jupiter's atmosphere would simply sink deeper and deeper into increasingly dense gas, the pressure and temperature climbing relentlessly, until the probe was crushed and vaporized. The Galileo atmospheric probe did exactly this in 1995, transmitting data for about 57 minutes before the conditions overwhelmed it. The critical takeaway here is that flyby, orbit, and landing each produce different travel times even when the destination is the same planet. A fast flyby of Jupiter might take roughly 13 months. An orbital mission to Jupiter might take 6 years because it follows a longer, more intricate path involving multiple gravity assists, arriving slowly enough to break into orbit without an impossibly large fuel supply. These are not the same mission, and they do not yield the same travel time. Confusing them is one of the most common mistakes people make when asking how long it takes to reach a planet. Now, here is something that surprises nearly everyone who learns about it for the first time. Reaching Mercury, one of the closest planets to Earth, is in many ways harder than reaching Jupiter, a world nearly 500 million kilometers away at its closest approach. This seems absurd. Mercury is right there, close to the Sun, much nearer to Earth than Jupiter by any measure of distance. How could it possibly be harder to get there? The answer runs straight back to orbital mechanics. A spacecraft leaving Earth starts with Earth's orbital speed of about 30 kilometers per second. To reach an outer planet like Jupiter, the spacecraft needs to speed up. It adds energy to its orbit, expanding it outward. You fire your engines in the direction you are already moving, and your orbit grows larger. But to reach Mercury, which orbits much closer to the Sun, the spacecraft needs to do the opposite. It must slow down. It must shed a huge amount of orbital energy to fall sunward. And shedding energy is just as expensive in terms of fuel as gaining it. Mercury orbits the Sun at an average distance of only about 58 million kilometers, much closer than Earth's roughly 150 million. To drop from Earth's orbit down to Mercury's using a simple Hohmann transfer, a spacecraft must surrender a large fraction of its velocity. The total delta V required to enter orbit around Mercury on a direct transfer is actually greater than the delta V required to enter orbit around Jupiter. That is a fact worth pausing on. It costs more energy to orbit Mercury than to orbit Jupiter. The physics is clear and the numbers do not lie. Mercury, despite being one of the closest planets to Earth, is one of the most fuel-expensive destinations in the entire solar system. This is why no mission to Mercury has ever taken the direct route. Instead, engineers design elaborate multi-year trajectories that use gravity assists, repeated close flybys of other planets, to gradually reshape the spacecraft's orbit and bleed off speed without burning precious fuel. The spacecraft swings past Venus and even Mercury itself multiple times, each encounter nudging the orbit a little closer to Mercury's and shedding a little more velocity. These gravity assist sequences are masterpieces of orbital engineering, but they take years to complete. The journey to Mercury becomes far longer than the straight line distance would suggest. Not because the spacecraft is slow, but because reaching Mercury efficiently requires a long, winding path through the inner solar system. There is a deeper lesson in all of this, one that applies to every planet from Mercury all the way out to Neptune. You cannot calculate travel time from distance alone. You need to know the mission type. You need to know the trajectory. You need to know whether the spacecraft is performing a flyby, entering orbit, or landing. You need to know what gravity assists are available along the way. You need to know the capability of the rocket launching the mission. And you need to know exactly when the mission launches, because the positions of the planets at that moment determine the geometry of the entire transfer. Change any one of these factors, and the travel time changes with it. Sometimes by months, sometimes by years. The solar system is not a static map with fixed distances printed between labeled dots. It is a dynamic system of moving bodies, each tracing its own elliptical path around the sun, each at a different speed, each constantly changing its distance from every other body in the system. Planning a mission to another planet is more like plotting an interception against a moving target while standing on another moving platform. And the only way to cross the gap is to reshape your own orbit around a central star using carefully timed engine burns and the gravitational fields of worlds you pass along the way. Consider the precision this demands. Mission planners must calculate exactly where the target planet will be, months or years into the future, accounting for the gravitational influence of every significant body in the solar system. They must plot a trajectory connecting Earth's position at launch with the planet's predicted position at arrival, including multiple gravity assists timed to the second. They must determine every engine burn. They must account for the spacecraft's changing mass as fuel is consumed, and factor in tiny perturbations from solar radiation pressure, asteroid gravity, and even the slow outgassing of the spacecraft's own materials. And they must accomplish all of this with enough precision that a vehicle traveling hundreds of millions or billions of kilometers arrives within a few kilometers of its intended target. The fact that humanity has done this successfully, navigating spacecraft to every planet in the solar system, is one of the most quietly astonishing achievements in the entire history of exploration. The minimum energy Hohmann transfer provides a useful theoretical baseline for travel times, but real missions almost never follow a pure Hohmann path. Some use slightly faster trajectories at the cost of more fuel. Others use gravity assists to bend and reshape their orbits without burning fuel at all, trading time for energy savings. Many missions combine both, using a sequence of engine burns and planetary flybys choreographed across years to achieve trajectories that would be utterly impossible with propulsion alone. The result is that every mission to a given planet has its own unique travel time, shaped by its own unique trajectory. Consider Mars alone. Over the past 6 decades, more than a dozen spacecraft have made the journey from Earth to the Red Planet. Not one of them has taken exactly the same amount of time as any other. Some arrived in a little under 7 months. Others needed closer to 9. A few stretched beyond 10. Every single transit was different because every single launch window placed Earth and Mars in a slightly different configuration. The planet was at a different point in its orbit. The geometry of the transfer ellipse was subtly changed. The arrival speed and approach angle shifted. No two missions flew the same path, because the solar system never presents the same arrangement twice. There is no single true answer to how long it takes to reach Mars. There's only the answer for that particular mission, that particular trajectory, that particular moment in the endless dance of planets around our star. And this variety only deepens as we move beyond Mars. When we turn our attention to Mercury and Venus in the inner solar system, then outward to the gas giants and the ice giants, the range of possible trajectories and travel times becomes even more dramatic. Some journeys last months, others last years, a few have spanned decades. The shortest are fast flybys where the spacecraft screams past its target at breathtaking speed. The longest are patient orbital missions that loop through the solar system for years, gathering speed or shedding it through repeated encounters with multiple planets before finally arriving at a destination that may have completed several full orbits around the Sun during the voyage. So as we now turn to the planets themselves and trace the actual journeys spacecraft have made to reach them, keep this framework firmly in mind. The planets are moving. The spacecraft is moving. Nothing travels in a straight line. Every interplanetary journey is a precisely calculated reshaping of an orbit, timed to intercept a world that will not be where it is right now by the time anything we launch can possibly arrive. Distance alone tells you almost nothing. What matters is orbital mechanics, the elegant, demanding, and sometimes deeply counterintuitive physics of moving through a solar system that never, ever stands still. Mercury sits closer to Earth than Jupiter, closer than Saturn, closer than any of the outer planets by a wide margin. At its nearest approach, Mercury can come within about 77 million kilometers of our planet. Jupiter, by comparison, never gets closer than roughly 588 million kilometers. The arithmetic could not seem more straightforward. Mercury is much closer, so it should be far easier and far faster to reach. But Mercury has humiliated that logic repeatedly across decades of space exploration, and the missions themselves tell the story better than any equation ever could. The first spacecraft to visit Mercury was Mariner 10, launched on the 3rd of November 1973. Mariner 10 could not fly directly to Mercury. No spacecraft in existence had the fuel to do what a direct transfer demanded. Dropping from Earth's orbit down to Mercury's requires shedding so much orbital velocity that the propellant budget for a direct insertion would have dwarfed anything the mission could carry. So engineers devised a different approach, one that had never been tried before. They aimed Mariner 10 at Venus first. On the 5th of February, 1974, roughly 3 months after launch, Mariner 10 swung past Venus at close range. As it fell through Venus's gravitational field, the planet's gravity bent the spacecraft's trajectory and reshaped its solar orbit, slowing it relative to the Sun and redirecting it inward toward Mercury. This was the first time in history that a gravity assist had been used to send a spacecraft to another planet. The technique worked beautifully. About 7 weeks after the Venus flyby, on the 29th of March, 1974, Mariner 10 swept past Mercury for the first time, roughly 5 months after leaving Earth. 5 months. That sounds fast. And for a flyby, it was fast. Mariner 10 screamed past Mercury at tremendous speed, snapping photographs and collecting measurements during a brief encounter. It could not slow down. It could not stop. It mapped roughly 45% of Mercury's surface across 3 separate flybys before its fuel ran out and contact was lost. But it never entered orbit. It never lingered. Each encounter lasted hours, not days, and then Mercury fell behind as the spacecraft continued along its own solar orbit. Mariner 10 proved that reaching Mercury quickly was possible if you were willing to accept a flyby. But actually orbiting Mercury, staying there, studying it over months and years, that was an entirely different problem. The challenge of orbiting Mercury fell to a mission called Messenger, and the journey it endured illustrates just how brutally difficult this destination truly is. Messenger launched on the 3rd of August, 2004. Its target was Mercury, a planet that at closest approach sits less than 80 million kilometers from Earth. And yet Messenger did not enter orbit around Mercury until the 18th of March, 2011. The journey took approximately 6 years and 7 months. Think about that for a moment. A spacecraft traveled for nearly 7 years to reach one of the closest planets in the solar system. The reason was gravity assists. Messenger could not carry enough fuel to fly to Mercury and break into orbit on its own. Instead, engineers designed one of the most intricate trajectories ever flown. After launch, Messenger first swung past Earth itself about a year later, using our own planet's gravity to reshape its orbit. Then it flew past Venus twice, once in October 2006 and again in June 2007, each time shedding more orbital energy and nudging its path closer to Mercury's orbit. Then came 3 separate flybys of Mercury itself, in January 2008, October 2008, and September 2009. Each Mercury flyby accomplished 2 things simultaneously. It gave scientists precious close-range data about the planet, photographs and measurements collected during each brief encounter, and it subtly altered the spacecraft's orbit, bleeding off a bit more speed each time, gradually matching Mercury's orbital path more closely. Only after 6 gravity assists spanning nearly 7 years was Messenger moving slowly enough relative to Mercury that a final engine burn could capture it into orbit. That engine burn lasted about 15 minutes and consumed roughly 30% of the spacecraft's total fuel supply. If the burn had failed, if the engine had misfired or shut down early, Messenger would have sailed past Mercury and into the void, and those 7 years of patient maneuvering would have been wasted. The burn succeeded. Messenger became the first spacecraft to orbit Mercury, and it studied the planet for more than 4 years before its fuel was finally exhausted, and it crashed into Mercury's surface in April 2015. The next mission to Mercury pushed the complexity even further. Bepi-Colombo, a joint mission between the European Space Agency and the Japan Aerospace Exploration Agency, launched on the 20th of October 2018. The mission is named after the Italian mathematician Giuseppe Colombo, who originally calculated the gravity assist trajectory that made Mariner 10's journey possible decades earlier. Bepi-Colombo carries 2 separate orbiters designed to study Mercury from complementary perspectives. One focused on the planet's surface and interior, the other on its magnetic field and surrounding space environment. The trajectory is staggering in its intricacy. 1 flyby of Earth, 2 flybys of Venus, 6 separate flybys of Mercury, 9 gravity assists in total, each one calculated with extraordinary precision, each one gradually slowing the spacecraft and reshaping its orbit over years of patient coasting. Bepi-Colombo is not expected to enter Mercury orbit until roughly 2026, making the total journey approximately 8 years. 8 years to reach a planet that, at its very nearest, is less than 80 million kilometers from Earth. No one would design a trajectory this long and this complex by choice. Engineers build these winding multi-year paths because the physics of reaching Mercury demands it. There is no shortcut. You either spend decades worth of fuel on a direct transfer, fuel that no existing rocket can provide, or you accept years of gravity assists, patiently trading time for the energy savings that make the mission possible at all. Mercury is the solar system's great paradox of proximity. Close in distance, remote in accessibility, the travel times tell the tale. A fast flyby can reach Mercury in roughly 5 months, but entering orbit, the kind of sustained presence that allows real scientific study, has required between 7 and 8 years for every mission that has attempted it. Mercury will almost certainly never be a quick trip, not with chemical rockets, and not without the patient gravitational assistance of the very planets the spacecraft passes along the way. Venus is a different story entirely. If Mercury punishes spacecraft for trying to reach it, Venus practically invites them in. Venus orbits closer to the Sun than Earth does, at an average distance of about 108 million kilometers from the Sun, compared to Earth's 150 million. When Venus and Earth align on the same side of the Sun, Venus can approach within roughly 38 million kilometers of our planet. That is closer than any other planet ever comes to Earth. And reaching Venus requires a relatively modest change in orbital energy compared to most other destinations. A spacecraft leaving Earth needs to slow down slightly to drop inward toward Venus's orbit, but the delta V involved is manageable, far less than what Mercury demands, and less even than what Mars requires for an orbital mission. The result is that Venus was the first planet ever successfully visited by a spacecraft, and the journey was remarkably short. Mariner 2 launched on the 27th of August, 1962, and flew past Venus on the 14th of December that same year. The transit took roughly 109 days, about 3.5 months. This was a historic achievement for reasons that went far beyond the flight itself. Mariner 2 was the first successful interplanetary mission in human history. Every previous attempt by both the United States and the Soviet Union had failed. Rockets had exploded on the launch pad. Spacecraft had lost contact. Missions had tumbled out of control. Mariner 2 broke through all of that and proved that humanity could actually send a functioning machine to another world and receive data back from it. And the journey itself was short enough that the mission team did not have to wait years for results. 3.5 months after launch, they had measurements from another planet. The Soviet Union took the next great leap. Throughout the 1960s and 70s, the Soviet Venera program pursued something far more ambitious than a flyby. They wanted to land on Venus, and Venus made that goal extraordinarily punishing. The planet's surface conditions are among the most hostile in the entire solar system. The atmosphere is almost entirely carbon dioxide, and it is crushingly thick. The pressure at the surface is about 90 times the pressure at sea level on Earth, roughly equivalent to the pressure you would experience at a depth of 900 meters beneath Earth's oceans. The temperature at the surface averages roughly 900 degrees Fahrenheit, hot enough to melt lead and to glow faintly red if you could somehow see through the dense atmosphere. Clouds of sulfuric acid hang in the upper layers. The surface is a scorched, barren hellscape where no human technology has ever survived for more than a few hours. The early Venera missions were destroyed long before reaching the surface. Venera 3 reached Venus in 1966, but its communication system failed during descent. Several more attempts followed, each one crushed or overheated during the plunge through that suffocating atmosphere. Finally, in December 1970, Venera 7 became the first spacecraft in history to successfully land on the surface of another planet. The transit from Earth had taken roughly 4 months. Venera 7 transmitted data from the surface for approximately 23 minutes before the conditions overwhelmed it. Those 23 minutes of data from a machine sitting on the surface of Venus, battered by 90 atmospheres of pressure and temperatures approaching 500 degrees Celsius, represented a triumph of engineering stubbornness. The Soviets kept pushing. Venera 9, arriving in October 1975 after a similar 4-month transit, sent back the first photographs from the surface of Venus. Venera 13, landing in March 1982, captured the first color photographs. It survived on the surface for about 127 minutes, longer than any other lander before or since. Every one of these missions traveled from Earth to Venus in roughly 4 months, a transit time that has remained fairly consistent across decades of missions. Venus is close. Venus is accessible. Getting there is not the problem. Surviving there is. More recently, the Magellan spacecraft, launched in May 1989, arrived at Venus in August 1990 after a journey of about 15 months. Magellan followed a longer trajectory than the Venera probes because it launched during a less favorable orbital window and carried the fuel needed to enter Venus orbit rather than simply crash into the atmosphere. Once in orbit, Magellan used radar to map nearly the entire surface of Venus through the thick clouds, revealing volcanoes, vast lava plains, and tectonic features hidden beneath the permanent overcast. The 15-month trip demonstrated the same lesson we encountered at Mercury. Orbit insertions often demand longer, less direct trajectories than flybys, because the spacecraft must arrive slowly enough for its engines to capture it. Venus will likely see renewed exploration in the coming decade. Missions under development aim to study the planet's atmosphere and surface in ways that earlier technology could not achieve. The transit times will remain short, probably 4 to 6 months depending on the launch window and mission design. The real challenge at Venus has never been getting there. It has always been enduring the inferno that waits on the other side of those sulfuric acid clouds. After decades of relative neglect, Venus is about to receive renewed attention. In 2021, NASA selected 2 new Venus missions for development. The first, called Da Vinci, will send a descent probe plunging through the Venusian atmosphere, measuring its composition in detail as it falls toward the surface over roughly an hour. The probe will sample atmospheric gases at different altitudes, searching for clues about how Venus's climate evolved from what may have been a temperate, ocean-bearing world billions of years ago into the suffocating furnace it is today. The transit from Earth to Venus will follow the same well-understood trajectory that earlier missions pioneered, likely arriving within 4 to 6 months, depending on the launch window. The second mission, called Veritas, will orbit Venus and use radar to map the planet's surface at far higher resolution than Magellan achieved in the early 1990s. Veritas will also measure surface elevation with enough precision to detect whether any volcanoes on Venus are actively erupting today. A question that has tantalized scientists for decades. Evidence from the European Space Agency's Venus Express mission, which orbited the planet from 2006 to 2014, hinted at possible recent volcanic activity, but the data were not conclusive. Veritas aims to settle the question. Da Vinci is expected to launch in the late 2020s or early 2030s, while Veritas has faced budget-related delays that have left its timeline uncertain. If both missions ultimately fly, their travel times will be measured in months, not years, a reminder that Venus remains one of the most accessible destinations in the solar system, even if its surface remains one of the most hostile. Now, Mars. If Venus is the planet that beckons you in and then tries to destroy you, Mars is the planet that makes you wait. Mars orbits farther from the Sun than Earth does, at an average distance of about 228 million kilometers. As we discussed, favorable launch windows for Mars open only once, roughly every 26 months. That rhythm has shaped the entire history of Mars exploration. Missions must be designed, built, and tested to meet a deadline that the planets themselves impose. If a spacecraft is not ready when the window opens, there is no launching a few weeks late or pushing the schedule back a quarter. You wait 26 months, and the alignment geometry of the next window will be slightly different, which may require changes to the entire trajectory. Every Mars mission begins with a calendar, and the calendar is written by orbital mechanics. Missions must be designed, built, and tested to meet a deadline that the planets themselves impose. If a spacecraft is not ready when the window opens, there is no launching a few weeks late or pushing the schedule back a quarter. You wait 26 months, and the alignment geometry of the next window will be slightly different, which may require changes to the entire trajectory. Every Mars mission begins with a calendar, and the calendar is written by orbital mechanics. Within those launch windows, the travel time to Mars varies depending on the specific alignment and the trajectory chosen. Minimum energy Hohmann-type transfers typically take roughly 8 to 9 months. Faster trajectories, which spend more fuel to follow a shorter path, can reduce this to about 6 or 7 months. The fastest missions to Mars have arrived in roughly 6.5 months. The slowest direct transfers have taken closer to 10 or 11 months. No two Mars missions take exactly the same amount of time, because no two launch windows present exactly the same geometry. Consider the contrast between a flyby and a landing. When the earliest Mars probes flew past the planet, they could accept whatever arrival speed their trajectory produced. They screamed past at kilometers per second, snapped photographs during a few hours of close approach, and continued into deep space. But landing on Mars demands a completely different approach. The spacecraft must not only reach Mars, but must arrive at a speed and angle that allows it to survive entry into the Martian atmosphere and touch down intact on the surface. Mars presents a uniquely cruel atmospheric challenge for landing. Earth's atmosphere is thick. A spacecraft returning from orbit can rely on atmospheric drag to shed most of its velocity, slowing from orbital speed to parachute deployment speed through friction alone. The atmosphere does most of the work, but Mars has an atmosphere less than 1% as dense as Earth's. It is thick enough to generate punishing heat during entry. A spacecraft hitting the upper Martian atmosphere at thousands of kilometers per hour compresses the thin air ahead of it into a superheated plasma, and the heat shield must absorb temperatures exceeding 1000 degrees Celsius. So the atmosphere creates enormous thermal stress, but it is too thin to slow the spacecraft sufficiently through drag alone. A parachute helps, but even the largest parachute ever deployed on Mars cannot reduce the vehicle's speed to anything close to a survivable landing velocity. The final phase requires rockets, retro thrusters that fire downward to break the lander through its last moments of descent. For the Curiosity rover, which landed in August 2012, and the Perseverance rover, which landed in February 2021, Engineers at NASA invented a landing system so audacious, it sounded like science fiction. After the heat shield absorbed the initial entry heat and a supersonic parachute slowed the vehicle further, a rocket-powered descent stage called the Sky Crane took over. This platform hovered above the Martian surface on its own thrust while lowering the rover on nylon cables, gently depositing it on the ground like a crane placing cargo on a loading dock. Once the rover's wheels touched soil, the cables were severed and the Sky Crane flew away to crash at a safe distance. The Sky Crane was invented because earlier landing methods could not handle the mass of a rover like Curiosity or Perseverance. But those earlier methods were ingenious in their own right and tell a fascinating story about how engineers have wrestled with Mars's thin atmosphere across generations of landers. Mars Pathfinder, which touched down on the 4th of July, 1997, used a radically different approach. After the heat shield and parachute slowed the vehicle, a cluster of solid fuel retro rockets fired briefly to arrest most of the remaining descent speed. Then, just meters above the surface, the lander was released inside a cocoon of giant airbags. It hit the Martian ground at roughly 50 kilometers per hour and bounced, not once, not twice, but roughly 15 times, each bounce carrying it farther across the rocky terrain before it finally rolled to a stop. The airbags deflated, the petals of the lander opened, and the tiny Sojourner rover rolled out onto the surface. It was, by any measure, a controlled crash wrapped in cushions. The Spirit and Opportunity rovers, landing in January 2004, used essentially the same airbag system. Both spacecraft survived impacts that would have destroyed any unprotected machine. Bouncing across the Martian surface in their protective cocoons before settling upright. The system worked beautifully for rovers weighing about 180 kilograms each. But Curiosity weighed roughly 900 kilograms, and Perseverance about 1,025. No airbag system could absorb the impact forces generated by a machine, that heavy striking the ground at speed. The physics simply did not scale. Engineers needed a way to set heavy rovers down gently with near zero vertical velocity, and the Sky Crane was the answer. The entire sequence from the top of the atmosphere to the surface took about 7 minutes. During those 7 minutes, the spacecraft executed dozens of critical steps autonomously, without any input from Earth. Because the distance between Earth and Mars imposed a communication delay that made real-time control impossible. At the time of the Perseverance landing, signals traveling at the speed of light took approximately 11 minutes to cross the gulf between the two planets. By the time mission controllers received the signal confirming that the spacecraft had contacted the top of the Martian atmosphere, the rover had already been sitting on the surface for several minutes, either intact and functioning or destroyed. There was nothing anyone on Earth could do to intervene. The spacecraft either succeeded on its own or it failed on its own. This communication delay also shapes the transit itself in subtle ways. During the months-long cruise from Earth to Mars, engineers can send commands and receive data, but every exchange carries a delay that grows as the spacecraft moves farther from Earth. Early in the journey, the delay might be only a few minutes. By the time the spacecraft approaches Mars, the delay can stretch to more than 20 minutes each way. Any problem must either wait for the slow loop of communication or be handled by the spacecraft's own onboard systems. The further the spacecraft travels from Earth, the more independent it must become. The Viking program demonstrated these challenges for the first time. Viking 1 launched in August 1975 and entered Mars orbit in June 1976, roughly 10 months later. It spent weeks orbiting, photographing the surface and searching for a safe landing site. The original site proved too rough when seen in detail from orbit, forcing engineers to select a new location and upload new commands through that maddening time delay. Viking 1 finally touched down on the 20th of July, 1976, nearly 11 months after leaving Earth. It was the first spacecraft to successfully land on Mars and transmit photographs from the surface. The images showed a rust-colored rocky desert stretching to the horizon under a butterscotch sky. A world recognizable, yet utterly alien. Since Viking, every generation of Marslanders and rovers has followed a broadly similar timeline. Mars Pathfinder launched in December 1996 and landed on the 4th of July, 1997, about 7 months after launch. The Spirit and Opportunity rovers, launched separately in June and July of 2003, each reached Mars in roughly 7 months. Curiosity flew for about 8 months and 11 days. Perseverance completed its transit in approximately 6 months and 19 days. The variation across these missions is real, but bounded. 6 to 9 months is the realistic range for a Mars journey with existing chemical propulsion, depending on the launch window and the trajectory chosen. But notice something crucial across all of these examples. The missions that fly past a planet are faster than the missions that orbit it, and the missions that orbit are often faster than the missions that land. A Mariner-class flyby of Mars can arrive in 7 months, but collects data for only hours. A Viking-class orbiter takes 10 months because it follows a trajectory designed to arrive at a lower relative speed, making orbital capture possible without an impossibly large fuel supply. A landing mission must not only reach orbit, but must then descend through the atmosphere, a process that imposes its own constraints on approach speed and geometry. This pattern holds across every planet from Mercury outward. Travel time is not just about distance. It is not just about trajectory. It is also about what you intend to do when you arrive. A fast flyby, a patient orbit, and a carefully controlled landing are 3 fundamentally different goals, and each one rewrites the timeline. The 3 inner planets we have examined each illustrate a different face of this reality. Mercury is close, but energetically punishing, demanding years of gravity assists just to enter orbit. Venus is close and energetically accessible, reachable in as little as 3.5 months. Yet its surface environment destroys anything that lands within hours. Mars is moderately distant and moderately accessible, reachable in 6 to 9 months. But its thin atmosphere turns every landing into a precisely choreographed gamble that the spacecraft must execute entirely on its own. As we now turn our attention outward, past the asteroid belt, toward the giant worlds of the outer solar system, the distances grow dramatically and the travel times stretch from months into years. But the principles remain the same: moving targets, curved trajectories, launch windows, gravity assists, and always the fundamental question that shapes every mission design. Are you flying past, entering orbit, or attempting to land? Because as we are about to see at Jupiter and Saturn, the answer to that question can mean the difference between a 13-month sprint and a 7-year odyssey. Beyond the asteroid belt, the solar system changes character. The rocky inner worlds give way to something entirely different. Enormous planets built not of stone and metal, but of gas and ice. Worlds so massive that their gravity reshapes the trajectories of everything that passes near them. Jupiter and Saturn dominate this outer realm, and reaching them has demanded some of the most ambitious voyages in the history of exploration. The distances are vast, the travel times stretch from months into years, and the difference between a fast flyby and a controlled orbit becomes not just significant, but staggering. Jupiter is the first world a spacecraft encounters after crossing the asteroid belt, and it is a destination unlike anything in the inner solar system. It is the largest planet orbiting our star, with a diameter of roughly 143,000 kilometers, more than 11 times the width of Earth. Its mass is greater than all the other planets combined. More than 300 Earths could fit inside it by mass, and roughly 1,300 by volume. Jupiter's gravity is so powerful that it has shaped the architecture of the entire solar system. It has flung asteroids and comets into new orbits, captured dozens of moons into its own gravitational embrace, and served as a kind of cosmic sentinel, deflecting or absorbing objects that might otherwise have struck the inner planets. And for spacecraft navigating the outer solar system, Jupiter's gravity is the single most important tool available. It is the greatest slingshot in the solar system, capable of bending trajectories and hurling spacecraft toward destinations that would otherwise be unreachable. But first, you have to get there. Jupiter orbits the Sun at an average distance of about 778 million kilometers, roughly 5.2 astronomical units. At its closest approach to Earth, when both planets are on the same side of the Sun and aligned favorably, Jupiter is still about 588 million kilometers away. At its most distant, with the Sun between them, the separation exceeds 900 million kilometers. A minimum energy Hohmann transfer from Earth to Jupiter takes roughly 2 years and 9 months. In practice, most missions have taken between 1.5 and 6 years, depending on the trajectory and mission objectives. The first spacecraft to reach Jupiter was Pioneer 10, launched on the 2nd of March, 1972. Pioneer 10 followed a relatively direct outbound trajectory, boosted by a powerful Atlas Centaur rocket that gave it enough velocity to reach Jupiter without gravity assist from other planets. It crossed the asteroid belt, the first spacecraft ever to do so, and arrived at Jupiter on the 3rd of December, 1973, approximately 21 months after launch. Pioneer 10 performed a fast flyby, sweeping past the planet at a closest approach distance of about 130,000 kilometers. It measured Jupiter's magnetic field, its radiation belts, and its atmosphere, returning the first close-range images of the giant planet. And then it kept going. Pioneer 10 had no means to slow down. Jupiter's gravity bent its trajectory, accelerating it further, and the spacecraft sailed onward into the outer solar system, eventually becoming one of the most distant human-made objects ever launched. Pioneer 11 followed about a year later, launching in April 1973 and arriving at Jupiter in December 1974 after a transit of roughly 20 months. Its flyby was closer and more daring than Pioneer 10's. Engineers deliberately aimed Pioneer 11 so that Jupiter's gravity would redirect it across the solar system toward Saturn, making it the first spacecraft to use Jupiter as a gravitational stepping stone to a more distant world. That encounter would prove historic in its own right. The Pioneer missions proved that the journey to Jupiter was achievable in less than 2 years with a direct, fast trajectory, but they also demonstrated the fundamental limitation of flybys. Each encounter lasted only hours. Pioneer 10's closest approach to Jupiter happened over the course of a single day. The spacecraft collected data frantically during those hours, transmitting everything it could back to Earth. And then Jupiter shrank behind it. There was no second pass, no lingering study, no ability to observe the planet's weather patterns evolve over weeks or months, no chance to make repeated close approaches to its fascinating moons. A flyby gives you a snapshot. For a portrait, you need an orbiter. The fastest flyby of Jupiter to date belongs to New Horizons, a mission designed not for Jupiter itself, but for Pluto. New Horizons launched on the 19th of January, 2006, departing Earth at roughly 58,000 kilometers per hour, making it the fastest spacecraft ever launched at that time. It reached Jupiter on the 28th of February, 2007, just 13 months and 9 days after leaving Earth. Barely over a year to cover the vast gulf between Earth and Jupiter. But New Horizons never intended to stay. The spacecraft screamed past Jupiter at tremendous speed, and Jupiter's gravity grabbed it and flung it onward even faster. The flyby accelerated New Horizons by roughly 14,000 kilometers per hour, bending its trajectory and hurling it toward the outer solar system at a velocity that no chemical rocket could have achieved on its own. New Horizons used Jupiter exactly the way a surfer uses a wave, borrowing the planet's own momentum to propel itself toward a destination far beyond. The encounter with Jupiter lasted a few intense weeks of observation, and then Jupiter was gone. New Horizons had years of silent coasting ahead before reaching Pluto. This is the power of a gravity assist, and understanding how it works is essential to understanding why outer planet travel times vary so dramatically. A gravity assist is not some mysterious trick. It is pure Newtonian physics. When a spacecraft approaches a planet, the planet's gravity accelerates the spacecraft, pulling it closer and speeding it up. As the spacecraft swings around the planet on a curved path, the planet's gravity continues to act on it. When the spacecraft exits the other side of the encounter, it has been redirected and its speed relative to the Sun has changed. The key insight is that the planet itself is moving. Jupiter orbits the Sun at about 13 kilometers per second. When a spacecraft swings behind Jupiter in its orbit, the planet's gravity effectively tows the spacecraft forward, transferring a tiny fraction of Jupiter's own orbital momentum to the spacecraft. From Jupiter's perspective, the spacecraft arrives at a certain speed and leaves at the same speed. No energy is created or destroyed during the encounter. But relative to the Sun, the spacecraft's velocity has changed dramatically because the entire interaction took place aboard a moving platform. A platform that happens to be a planet traveling at 13 kilometers per second. The spacecraft borrows momentum from the planet. The planet, in exchange, slows down by an amount so vanishingly small that it is utterly undetectable. Jupiter's mass is so enormous that lending a few thousand kilometers per hour of velocity to a small spacecraft costs it nothing measurable. The planet does not even notice. Jupiter is the most powerful gravity assist source in the solar system because it is the most massive planet. Its gravitational field extends farther and pulls harder than any other world orbiting our star. A well-designed Jupiter flyby can change a spacecraft's velocity by 10, 15, even 20 kilometers per second, and it can redirect the trajectory by large angles, aiming the spacecraft toward Saturn, Uranus, Neptune, or even out of the solar system entirely. No other planet comes close to offering this kind of gravitational leverage. This is why Jupiter appears in the trajectory of almost every mission to the outer solar system. It is the gateway, the on-ramp to the distant planets. Without Jupiter's gravity, reaching Saturn would require far more fuel. Reaching Uranus or Neptune with the current technology would be borderline impossible. But there is a critical distinction between using Jupiter for a gravity assist and actually staying at Jupiter. New Horizons reached Jupiter in 13 months, but never entered orbit. Galileo, the first and so far only spacecraft to orbit Jupiter, took roughly 6 years to get there. And the difference illustrates the central trade-off of outer planet exploration. Galileo launched on the 18th of October, 1989. Its destination was Jupiter, the same planet that Pioneer 10 had reached in 21 months, and New Horizons would later reach in 13. But Galileo's mission was fundamentally different. It was designed to enter orbit around Jupiter and study the planet, its atmosphere, and its moons over a period of years. This meant that Galileo could not arrive at Jupiter moving at tremendous speed. If it arrived too fast, no engine burn could slow it enough to be captured by Jupiter's gravity. The spacecraft would swing past and escape, just as the Pioneers had done. And the mission would be reduced to a brief flyby rather than the years-long orbital survey it was designed to accomplish. To arrive at Jupiter slowly enough for orbital capture, Galileo followed a long and winding path through the inner solar system first. It flew past Venus once in February 1990, using Venus's gravity to reshape its orbit. Then it swung back past Earth twice, once in December 1990 and again in December 1992, each encounter further modifying its trajectory and adding velocity. The sequence was Venus, Earth, Earth, a gravity assist chain that gradually built up the energy needed to reach Jupiter while keeping the arrival speed manageable. This indirect route through the inner solar system added years to the journey. Galileo did not arrive at Jupiter until the 7th of December, 1995, more than 6 years after launch. When it finally reached Jupiter, Galileo executed a critical orbital insertion burn. The spacecraft's main engine fired for about 49 minutes, slowing the vehicle enough for Jupiter's gravity to capture it into a highly elongated orbit. This single engine burn was one of the most nerve-wracking moments in the history of planetary exploration. If the engine had failed, 6 years of travel and over $1 billion of investment would have been lost. The burn succeeded, and Galileo spent the next 8 years orbiting Jupiter, making repeated close passes of the planet's 4 largest moons. Those moons, Io, Europa, Ganymede, and Callisto, proved to be among the most fascinating worlds in the solar system. Io turned out to be the most volcanically active body ever observed, its surface constantly reshaped by eruptions driven by the tidal forces of Jupiter's immense gravity. Europa revealed a smooth, icy shell, crisscrossed with fractures, beneath which lies a global ocean of liquid water that may contain more water than all of Earth's oceans combined. Ganymede, larger than the planet Mercury, was confirmed to have its own magnetic field, the only moon in the solar system known to possess one. None of these discoveries would have been possible with a flyby. They required years of repeated close encounters, dozens of orbits, thousands of photographs, and sustained measurement campaigns. They required an orbiter, And getting that orbiter to Jupiter demanded 6 years of patient, indirect travel through the inner solar system, a journey more than 4 times longer than Pioneer 10's direct dash. The Juno spacecraft, launched in August 2011, further demonstrated this trade-off. Juno's primary mission was to study Jupiter's atmosphere, interior structure, and magnetic field from a polar orbit. It launched during a favorable window and followed a trajectory that included an Earth gravity assist in October 2013, roughly 2 years after launch. Juno arrived at Jupiter on the 4th of July 2016, about 5 years after leaving Earth. Its orbital insertion burn lasted 35 minutes and had to execute flawlessly. There was no backup. Like Galileo, Juno carried just enough fuel for one chance at orbital capture. The burn succeeded, and Juno entered a highly elongated polar orbit that carries it from a few thousand kilometers above Jupiter's cloud tops out to several million kilometers, and back again on each revolution. Saturn, the 6th planet from the Sun, lies roughly twice as far from Earth as Jupiter does. At its closest approach, Saturn is about 1.2 billion kilometers away. At its most distant, the separation exceeds 1.6 billion kilometers. A minimum energy Hohmann transfer to Saturn takes approximately 6 years, but no mission has ever followed a pure Hohmann path to Saturn. Every spacecraft that has visited the ringed planet has relied on gravity assists, primarily from Jupiter, to make the journey feasible. Pioneer 11 was the first. After its Jupiter flyby in December 1974, Jupiter's gravity redirected Pioneer 11 on a long arcing trajectory across the solar system toward Saturn. The spacecraft arrived at Saturn on the 1st of September 1979, about 6.5 years after its original launch from Earth. It was the first close-range encounter with Saturn, returning images of the planet's rings, its atmosphere, and several of its moons. But like the Pioneer Jupiter flybys, the encounter was brief. Pioneer 11 swept past at high speed, collected what data it could during a few hours of close approach, and continued outward into interstellar space. Voyager 1 followed, and its trajectory demonstrated the extraordinary power of a well-planned Jupiter gravity assist. Voyager 1 launched on the 5th of September 1977, about 2 weeks after its twin Voyager 2. Despite launching second, Voyager 1 was placed on a faster trajectory and reached Jupiter first in March 1979, roughly 18 months after launch. Jupiter's gravity then flung Voyager 1 outward towards Saturn. The spacecraft arrived at Saturn on the 12th of November 1980. Approximately 3 years and 2 months after leaving Earth. 3 years and 2 months. Compare that to Pioneer 11's 6.5 years. Voyager 1 reached Saturn in roughly half the time because it launched during a more favorable planetary alignment and used a more aggressive Jupiter gravity assist that hurled it towards Saturn at higher speed. The difference was entirely about trajectory design and timing, the positions of the planets at launch, and the geometry of the Jupiter flyby. Same destination, same type of mission, vastly different travel times. Orbital mechanics dictated both, and the planet's positions at the moment of launch made all the difference. Voyager 1's Saturn encounter was also a turning point. Engineers had designed the trajectory so that the spacecraft could make a close flyby of Titan, Saturn's largest moon, and one of the most intriguing worlds in the solar system. Titan is the only moon known to possess a thick atmosphere, a dense, nitrogen-rich blanket even denser than Earth's. Scientists desperately wanted a close look. The Titan flyby succeeded magnificently, returning data that would fuel decades of research. But the geometry required for the Titan encounter aimed Voyager 1 sharply out of the plane of the solar system after Saturn. There would be no further planetary encounters. Voyager 1's mission as a planetary explorer ended at Saturn, and it began its long solitary journey into interstellar space. Voyager 2, meanwhile, followed a different path to Saturn, arriving in August 1981, roughly 4 years after launch. Its trajectory was designed not just for Saturn, but for what lay beyond. Voyager 2 would continue onward to Uranus and Neptune, a journey unlike anything attempted before or since. The crucial point is that Voyager 2's Saturn trajectory was deliberately slower and less direct than Voyager 1's, because it had to set up the geometry for those subsequent encounters. Reaching Saturn was not the end of the journey, but a waypoint. Every trajectory decision at Saturn was made with Uranus in mind, and every decision at Uranus was made with Neptune in mind. The entire mission was a single continuous chain of gravity assists, each one precisely calculated to enable the next. The most ambitious Saturn mission ever flown was Cassini, and its journey illustrates every principle of outer planet travel we have discussed. Cassini was designed to enter orbit around Saturn and study the planet, its rings, and its moons for years. It carried the Huygens probe, built by the European Space Agency, which would detach from the orbiter and descend through Titan's atmosphere to the surface. No mission to Saturn had ever attempted anything like this, and the trajectory required to make it possible was one of the most complex ever devised. Cassini launched on the 15th of October, 1997. Its first destination was not Saturn, but Venus. On the 26th of April, 1998, about 6 months after launch, Cassini swung past Venus for the first time. The flyby reshaped Cassini's solar orbit and sent it looping back for a second Venus flyby on the 24th of June, 1999. Then came an Earth flyby on the 18th of August, 1999. Then a long coast outward to Jupiter, where Cassini performed a gravity assist on the 30th of December, 2000. Venus, Venus, Earth, Jupiter. 4 gravity assists across 3 years before the spacecraft even began its final approach to Saturn. Each flyby was calculated with extraordinary precision. Each one nudged Cassini's orbit, adding energy, reshaping the trajectory, building toward the velocity needed to reach Saturn at a manageable arrival speed. Cassini finally arrived at Saturn on the 1st of July, 2004, approximately 6 years and 9 months after launch. Its orbital insertion burn lasted 96 minutes, the longest and most critical engine firing of the entire mission. The spacecraft passed through a gap in Saturn's rings during the burn, a calculated risk that brought it close enough to Saturn for the maneuver to work with the available fuel. If the engine had failed, or if a ring particle had struck the spacecraft during those 96 minutes, the mission would have ended. The burn succeeded. Cassini spent the next 13 years orbiting Saturn, making 294 orbits of the planet, performing 127 close flybys of Titan, and making countless observations of the rings, the atmosphere, and the smaller moons. On the 25th of December 2004, the Huygens probe separated from Cassini and began a 20-day coast toward Titan. On the 14th of January 2005, it plunged into Titan's atmosphere and descended to the surface, transmitting data for roughly 72 minutes after touchdown. The images from the surface showed a landscape of rounded ice pebbles resting on a dark, damp plain. A world where liquid methane plays the role that water plays on Earth. Enceladus, a small icy moon only about 500 kilometers in diameter, proved to be one of Cassini's greatest discoveries. Geysers at the moon's south pole were observed shooting plumes of water ice and vapor hundreds of kilometers into space. The water originates from a subsurface ocean hidden beneath the icy crust. Cassini flew directly through these plumes and detected organic molecules, complex carbon-based chemistry that represents the building blocks of life. Enceladus is now considered one of the most promising locations in the solar system for the search for extraterrestrial life. None of these discoveries would have been possible without an orbiter. A flyby would have captured a few images of Enceladus and moved on. It took years of repeated close passes, carefully targeted by adjusting Cassini's orbit around Saturn, to reveal what this small moon was hiding. The contrast in travel times across all these Saturn missions is striking. Pioneer 11 took about 6.5 years. Voyager 1, benefiting from a more favorable alignment and a powerful Jupiter assist, arrived in about 3 years and 2 months. Voyager 2 took roughly 4 years. Cassini needed nearly 7 years because its complex gravity assist chain through the inner solar system, while essential for an orbital mission, added years to the journey. The destination was the same in every case. The travel times ranged from about 3 years to nearly 7. The difference was trajectory, timing, and mission type. And this pattern reveals a truth that applies to every planet from Mercury to Neptune. Asking how long it takes to reach a planet is like asking how long it takes to cross an ocean. By speedboat, by sailing ship, by cargo freighter, or by swimming. Each method crosses the same water. Each arrives at the same shore. But the journey times are vastly different because the means and the purpose are different. A fast flyby of Jupiter can arrive in 13 months. An orbital mission might take 5 or 6 years. A fast flyby of Saturn arrived in about 3 years. An orbital mission took nearly 7. These are not contradictions. They are different answers to different questions, and every answer is correct within the context of its own mission. The gas giants also reveal something profound about the nature of exploration itself. Every spacecraft that has visited Jupiter or Saturn has expanded human knowledge immeasurably, but the deeper the engagement, the richer the return. The pioneers gave us our first glimpse. The Voyagers gave us panoramic surveys. Galileo and Cassini gave us years of intimate, detailed study that transformed our understanding of these worlds and their moons. Each step demanded more time, more patience, and more complex engineering. Each step rewarded that investment with discoveries that the faster, simpler missions could never have made. The gravitational slingshots provided by Jupiter and Saturn also carry spacecraft outward toward even more distant targets. Voyager 2 used both planets as stepping stones on its way to Uranus and Neptune. New Horizons used Jupiter to catapult itself toward Pluto. Every mission to the outermost reaches of the solar system has relied on gravity assists from the gas giants to make the journey possible within a human career span. Without these gravitational boosts, the ice giants and the dwarf planets beyond them would remain largely out of reach, their travel times stretching into decades that would test the patience and the budget of any space agency on Earth. As we now look beyond Saturn, past the familiar gas giants and into the cold, dim reaches where Uranus and Neptune orbit in near darkness, the distances grow once more and the challenges deepen. The ice giants have been visited only once each, by a single spacecraft that flew past them decades ago and never returned. Their stories are stories of extraordinary patience, unrepeatable planetary alignments, and journeys so long that the engineers who designed them were not the same people who celebrated their arrival. The outermost planets demand something that no amount of technology can replace: time. Uranus orbits the Sun at an average distance of roughly 2.9 billion kilometers, about 19 astronomical units from our star. Neptune sits even farther out at approximately 4.5 billion kilometers, roughly 30 astronomical units. These are distances so enormous that the sunlight reaching Uranus is only about 1/400th as intense as the sunlight on Earth, and Neptune receives roughly 1/900th. Out here, the Sun is no longer the blazing disk that dominates Earth's daytime sky. It is a brilliant point of light, brighter than any star but no longer recognizable as the furnace that warms the inner planets. The ice giants live in permanent twilight at the cold, dim edge of the planetary system. Both Uranus and Neptune have been visited exactly once. One spacecraft reached both of them, and the story of how it got there is one of the most remarkable achievements in the history of exploration. In the late 1960s, an aerospace engineer named Gary Flandreau, working at the Jet Propulsion Laboratory in California, noticed something extraordinary in the upcoming orbital positions of the outer planets. Jupiter, Saturn, Uranus, and Neptune were approaching an alignment that would allow a single spacecraft, launched in the late 1970s, to fly past all 4 giant planets, one after another. Each planet's gravity would bend the spacecraft's trajectory and accelerate it onward towards the next target. The alignment was rare. It occurs approximately once every 175 years. The last time these planets had been arranged this favorably, Thomas Jefferson had just entered the White House, and Napoleon was consolidating power in France. The next time they will align this way, it will be the middle of the 22nd century. NASA recognized the opportunity and designed what became the Voyager program. 2 spacecraft, Voyager 1 and Voyager 2, launched in the summer of 1977. Voyager 1 was aimed at Jupiter and Saturn with the trajectory optimized for a close flyby of Saturn's moon Titan. That Titan encounter, as we discussed, redirected Voyager 1 out of the plane of the solar system, ending its planetary mission at Saturn. But Voyager 2 was placed on a different, slower path, one carefully designed to preserve the geometry needed for the full grand tour. Jupiter, then Saturn, then Uranus, then Neptune. 4 planets, 1 spacecraft, 12 years of flight. Voyager. 2 reached Jupiter in July 1979, roughly 2 years after launch. Jupiter's gravity flung it onward. It reached Saturn in August 1981, about 4 years after launch. Saturn's gravity reshaped its trajectory once more, aiming it toward a patch of empty space where Uranus would be years later. And then Voyager 2 fell silent, in a sense. Not literally. It continued transmitting data and receiving commands. But for the next 4.5 years, it simply coasted through the void between Saturn and Uranus, crossing a gulf of over 1 billion kilometers with nothing to see and nothing to encounter. The engineers who monitored it waited. The scientists who had designed its instruments waited. The entire planetary science community waited. There was nothing to do but let physics carry the spacecraft onward across the vast emptiness of the outer solar system. On the 24th of January, 1986, approximately 8.5 years after leaving Earth, Voyager 2 swept past Uranus. The encounter was brief and fast. Voyager 2 passed within about 81,000 kilometers of the planet's cloud tops, traveling at roughly 60,000 kilometers per hour relative to Uranus. The spacecraft had a few hours of close-range observation. That was all. There was no slowing down, no entering orbit, no lingering. Every photograph, every measurement, every data point had to be collected during that fleeting passage and transmitted back to Earth across a distance of roughly 3 billion kilometers. The radio signals, traveling at the speed of light, took approximately 2 hours and 45 minutes to reach mission control. By the time engineers received confirmation that the closest approach had occurred, Voyager 2 was already receding from Uranus, never to return. What Voyager 2 found was a world unlike anything encountered before. Uranus is tilted on its side, its axis of rotation inclined roughly 98 degrees from vertical. No other planet has such an extreme tilt. Its magnetic field is offset from the planet's center and tilted at a steep angle to the rotational axis, creating a magnetosphere that tumbles through space in a corkscrew pattern. Voyager 2 discovered 10 previously unknown moons and found that Uranus's thin ring system, detected from Earth only 9 years earlier, was more complex than anyone had realized. The planet's atmosphere appeared eerily bland in visible light, a nearly featureless blue-green sphere. But this smooth exterior concealed dynamic weather patterns that later telescopes would begin to reveal. But perhaps the most astonishing discovery at Uranus was not the planet itself. It was Miranda, the smallest and innermost of the 5 major moons. Miranda is only about 470 kilometers across, small enough to fit comfortably inside the borders of a medium-sized country. By all expectations, a moon that Tiny should have been a dead, cratered ball of ice, geologically inert for billions of years. Instead, Voyager 2's cameras revealed a surface that looked as though it had been assembled from mismatched pieces of completely different worlds. Enormous canyons, some more than 10 times deeper than the Grand Canyon on Earth, scarred the moon's face. Vast chevron-shaped ridges cut across smooth plains. Regions of ancient, heavily cratered terrain sat directly beside younger, grooved landscapes that appeared to have been resurfaced by some geological process that no one fully understood. One feature, an immense cliff face now called Verona Rupes, may drop somewhere between 5 and 10 kilometers from top to bottom, making it likely the tallest known cliff in the solar system. The precise height remains uncertain because Voyager 2 captured limited imagery during its brief flyby. But even at the lower end of those estimates, if you stood at the edge and dropped a stone, it would take roughly 6 minutes to reach the bottom in Miranda's feeble gravity, drifting downward in slow motion rather than plummeting the way it would on Earth. Scientists have debated what could have produced such a bizarre surface. The leading hypothesis is that Miranda was shattered by a massive impact and then gravitationally reassembled, its fragments settling back together in a jumbled patchwork. Others suggest tidal heating from Uranus may have driven internal geological activity. The question remains open because no orbiter has ever returned. And then Voyager 2 was gone, its trajectory already curving toward Neptune. 3.5 more years of silent coasting lay ahead. 3.5 years of crossing another 1.5 billion kilometers of empty space, guided by nothing but the trajectory that Saturn and Uranus had given it. On the 25th of August, 1989, Voyager 2 reached Neptune. The journey from Earth had taken just over 12 years. 12 years. Stop and consider what that means in human terms. An engineer who joined the Voyager team as a young professional at launch would have been approaching middle age by the time the spacecraft reached Neptune. Children born the year Voyager 2 launched would have been 12 years old, starting middle school, when the spacecraft finally arrived at the most distant planet in the solar system, Voyager. 2 passed within roughly 5,000 kilometers of Neptune's cloud tops, the closest flyby of any planet during the entire Voyager mission. Neptune turned out to be far more dynamic than Uranus. Despite receiving almost no heat from the distant sun, Neptune generates more internal heat than it absorbs from sunlight, and this energy drives the fastest sustained winds measured on any planet. Wind speeds exceeding 2,000 kilometers per hour were recorded. A massive storm system dubbed the Great Dark Spot, reminiscent of Jupiter's Great Red Spot, dominated the southern hemisphere. Voyager 2 also made a close pass of Triton, Neptune's largest moon, and discovered something no one expected on a world so distant and so cold. Active geysers erupting from beneath the frozen crust. Triton orbits Neptune backward, in the opposite direction of the planet's rotation. Strong evidence that it was not born alongside Neptune, but was captured from the Kuiper Belt, the band of icy objects beyond Neptune's orbit. Triton deserves special attention because it is one of the most geologically active worlds ever observed in the outer solar system. Its surface temperature sits at roughly minus 235 degrees Celsius, making it one of the coldest measured surfaces of any body we have visited. And yet, Voyager 2 photographed dark plumes of nitrogen gas and fine dark particles rising as high as 8 kilometers above the surface, before being swept sideways by thin winds in Triton's tenuous atmosphere. These are genuine geysers, driven by solar heating of subsurface nitrogen ice that vaporizes and erupts through cracks in the frozen crust. The dark streaks they leave behind stain the bright, icy surface for kilometers downwind. Triton's surface is also remarkably young in geological terms. Very few impact craters are visible, which means the surface is being continuously renewed by some internal or surface process, cryovolcanism, glacial flows of nitrogen ice, or something else entirely. Some scientists now suspect that Triton, like Enceladus and Europa, may harbor a subsurface ocean of liquid water beneath its icy exterior, maintained by the residual heat of tidal interactions with Neptune. If that is true, Triton joins a growing list of worlds in the outer solar system where liquid water exists beneath ice. Worlds that might, in principle, harbor conditions suitable for life. And with Neptune behind it, Voyager 2's planetary mission ended. Like its twin, it continued outward, transmitting data from the increasingly remote frontier of the solar system. As of the mid-2020s, Voyager 2 is more than 20 billion kilometers from Earth. Still communicating, still sending back measurements of the interstellar medium, the thin gas and magnetic fields that fill the space between stars. Its radio signals, traveling at the speed of light, now take more than 18 hours to reach Earth. The fact that Uranus and Neptune have each been visited only once, and only by a spacecraft flying past at high speed, is one of the great frustrations of planetary science. Both worlds remain largely mysterious. We know more about Jupiter's moons than we know about either ice giant, an orbiter at Uranus or Neptune, something capable of spending years studying the planet, its rings, its moons, and its magnetosphere, would transform our understanding. But no such mission has flown, and the reasons are straightforward: distance and time. A dedicated orbiter for Uranus would need to travel roughly 3 billion kilometers and arrive slowly enough to be captured into orbit. Without the once-in-175-year Grand Tour alignment, there is no convenient chain of gravity assists connecting all 4 outer planets. A realistic Uranus orbiter launched in the 2030s might rely on a single Jupiter gravity assist, and then coast for a decade or more before arriving. Total mission time from launch to orbit insertion could easily reach 12 to 15 years. A Neptune orbiter would be even longer, potentially 15 to 20 years from launch to arrival. These are missions that span careers. An engineer who helps design the spacecraft may well retire before it reaches its destination. The scientific community must commit funding, maintain infrastructure, and sustain institutional knowledge across decades. These are not merely technical challenges, they are human challenges, tests of patience and dedication that push against the rhythms of careers, budgets, and political cycles. Despite these hurdles, proposals exist. A Uranus orbiter and probe mission has been identified as a high priority by the planetary science community. The concept envisions a spacecraft that would enter orbit around Uranus, deploy an atmospheric probe to descend into the planet's cloud layers, and spend years studying the Uranian system. The mission would likely launch no earlier than the mid-2030s, and would not arrive at Uranus until the late 2040s. An entire generation of scientists would grow up waiting for the data. Beyond the 8 planets lies a world that once held planetary status and lost it. Pluto orbits the Sun at an average distance of roughly 5.9 billion kilometers, about 39 astronomical units. Its orbit is highly elliptical and tilted relative to the plane in which the 8 planets travel. At times, Pluto actually comes closer to the Sun than Neptune does, though the 2 orbits are angled in a way that prevents an actual collision. Pluto is small, only about 2,376 kilometers across, smaller than Earth's moon. For 76 years after Clyde Tombaugh discovered it in 1930, Pluto was considered the 9th planet. But in 2006, the International Astronomical Union formally defined the word planet, and Pluto did not meet all the criteria. To qualify as a planet under the new definition, an object must orbit the Sun, must be massive enough for its own gravity to pull it into a roughly spherical shape, and must have cleared the neighborhood around its orbit of other debris. Pluto satisfies the first 2 conditions, but fails the third. Its orbit passes through the Kuiper Belt, a vast region populated by thousands of icy bodies left over from the solar system's formation. Pluto has not cleared this region. It shares its orbital neighborhood with many other objects. Several other Kuiper Belt objects are comparable in size. Eris, discovered in 2005, is slightly more massive than Pluto. Haumea and Makemake are also classified as dwarf planets. Reclassifying Pluto was controversial and remains a source of debate, but the scientific reasoning is clear. Pluto is one member of a large population of similar icy worlds, not a solitary planet that dominates its orbital zone. Reaching Pluto required one of the fastest and longest missions ever attempted. New Horizons, the same spacecraft that had used Jupiter as a slingshot roughly 8 years earlier, arrived at Pluto on the 14th of July, 2015, 9 years, 5 months, and 25 days after leaving Earth. Even at the tremendous speed it carried from launch and from the Jupiter gravity assist, the crossing still took nearly a decade. New Horizons performed a fast flyby at roughly 49,000 kilometers per hour relative to Pluto's surface. The encounter was brief. New Horizons had about a day of close-range observation as it swept through the Pluto system, photographing Pluto and its largest moon Charon with breathtaking detail. The images revealed a world far more complex than anyone had expected. Pluto's surface showed vast plains of nitrogen ice, mountain ranges made of water ice standing kilometers high, evidence of recent geological activity, and a thin but detectable atmosphere of nitrogen, methane, and carbon monoxide. The famous heart-shaped feature, informally named Tombor Regio after Pluto's discoverer, turned out to be a basin filled with slowly churning nitrogen ice. A landscape shaped by processes unlike anything seen elsewhere in the solar system. Charon, roughly half Pluto's diameter, showed deep canyons and a reddish polar cap, suggesting a complex geological history of its own. New Horizons transmitted its data back to Earth over the following 16 months. The spacecraft was so far away that the radio signal, even traveling at the speed of light, took about 4.5 hours to reach Earth. The data rate was painfully slow. Images that a smartphone could download in seconds required hours or days to trickle back across 5 billion kilometers of space. But every byte was precious. This was the first and so far only close-up look humanity has ever had at Pluto, a world so distant that the sun from its surface appears as little more than an extraordinarily bright star. The travel times we have traced across the solar system, from Mercury's paradoxical 7-year orbital journey to Pluto's 9.5-year sprint, all share a common constraint. Every one of them was achieved with chemical rockets, engines that burn liquid fuel and oxidizer to produce thrust. Chemical propulsion has carried humanity to every world we have visited. But chemical rockets have fundamental limits. The energy stored in chemical bonds places a ceiling on how much velocity change a given amount of fuel can provide. This ceiling is why gravity assists are so essential for outer-planet missions. Chemical rockets simply cannot carry enough fuel to reach distant destinations quickly on their own. But alternative propulsion technologies exist, and some have already been tested in deep space. Ion drives, also called solar electric propulsion, work by ionizing a propellant, typically xenon gas, and accelerating the ions to extremely high speeds using electric fields. The thrust produced by an ion drive is tiny, far too weak to lift a spacecraft off a launch pad. An ion engine produces about the same force as the weight of a sheet of paper resting on your hand. But it can run continuously for months or years, gradually building velocity in a way that chemical rockets, which burn for minutes and then go silent, cannot match. Over time, that gentle, continuous push adds up to enormous total velocity changes. NASA's Dawn spacecraft, launched in 2007, used ion propulsion to visit 2 separate destinations in the asteroid belt, orbiting the asteroid Vesta and then traveling onward to orbit the dwarf planet Ceres. No chemical rocket mission could have orbited both objects on a single fuel supply. The ion drive made it possible by providing efficient, sustained thrust across years of flight. Dawn's success proved that ion propulsion works for deep space exploration, and the technology has continued to improve. Newer ion engines like the Next-C thruster produce more thrust and operate more efficiently than Dawn's system. The European Space Agency and Japan's Bepi Colombo mission to Mercury also use electric propulsion alongside chemical engines, relying on ion thrusters during long cruise phases to gradually adjust its trajectory between gravity assists. This hybrid approach is becoming increasingly common in mission design. The key advantage is cumulative. A chemical engine provides a sharp, powerful burst lasting minutes. An ion engine provides a whisper of force lasting months. Over a journey of years, that whisper adds up to a velocity change that no single chemical burn could match on the same fuel budget. Psyche, a NASA mission launched in October 2023 toward a metal-rich asteroid of the same name, carries solar electric Hall effect thrusters that will propel it across roughly 3.5 billion kilometers over nearly 6 years. The spacecraft uses enormous solar arrays spanning roughly 75 square meters to generate the electricity that powers its thrusters. Psyche represents the largest solar electric propulsion system ever flown in deep space and is a proving ground for the technology that future outer planet missions will rely on. Nuclear electric propulsion takes the concept further. Instead of relying on solar panels to generate the electricity that powers the ion drive, a nuclear reactor provides the energy. This is especially important in the outer solar system, where sunlight is too faint for solar panels to produce meaningful power. A nuclear electric spacecraft could run its ion engines continuously for years, even decades, far from the sun, gradually building up velocity that no chemical rocket could match. Studies have shown that a nuclear electric spacecraft could reach Jupiter in as little as 2 years, roughly half the time of a conventional trajectory. A mission to Neptune might take 8 to 10 years instead of 12 or more. These are meaningful reductions that could bring the ice giants within reach of dedicated orbiters launched within a single scientist's career. Solar sails represent yet another approach. Instead of burning fuel or ionizing gas, a solar sail uses the pressure of sunlight itself to propel a spacecraft. Photons from the sun carry momentum, and when they strike a large reflective surface, they push it gently but continuously. The acceleration is extremely small near Earth's distance from the sun, but closer to the sun, the pressure increases dramatically. Some proposals envision launching a solar sail spacecraft on a trajectory that dips very close to the sun, collecting an enormous burst of radiation pressure, and then riding that momentum outward at high speed. Theoretical studies suggest that a solar sail with a close solar flyby could reach the outer solar system significantly faster than any chemical rocket, potentially cutting transit times to the ice giants by half or more. These technologies are not science fiction. Ion drives have flown. Solar sails have been deployed and tested in space. Nuclear electric propulsion has been studied extensively and is under active development, but none of them is ready to replace chemical rockets for primary planetary missions today. They represent the next generation of propulsion, technologies that will gradually reshape what is possible over the coming decades. When they mature, the travel times that have defined our exploration of the solar system, the 7-month Mars transits, the 6-year Jupiter orbiters, the 12-year Neptune flybys, may shorten considerably, but they will never shrink to nothing. The solar system is vast, and no propulsion technology can change that fundamental reality. It can only change how quickly we cross the distances that the planet's orbits impose. So, what is the honest answer to the question we began with? How long does it actually take to reach each planet? The honest answer is a range, not a single number, and the range depends on mission type, trajectory, launch window, and propulsion. Mercury. A flyby can arrive in as little as 5 months, but entering orbit has required 7 to 8 years of gravity assists. Venus. 3.5 months for a fast flyby, up to 15 months for an orbital mission. Mars. 6 to 9 months with chemical propulsion, depending on the launch window and trajectory. Jupiter. As fast as 13 months for an unpowered flyby, 5 to 6 years for an orbiter. Saturn. Roughly 3 years with a powerful Jupiter assist, up to 7 years for an orbital mission with multiple gravity assists. Uranus. The only visit took about 8.5 years as part of a multi-planet flyby chain. Neptune. Roughly 12 years, exploiting a planetary alignment that will not recur for nearly 2 centuries. Pluto. About 9.5 years for the fastest trajectory ever launched toward the outer solar system. These numbers are not fixed. They are snapshots of what has been achieved and what current physics allows. Future propulsion systems will change them. Different launch windows will shift them. New gravity assist strategies will reshape them. No single number captures the truth for any destination, because the truth is that every journey through the solar system is unique, shaped by the positions of moving worlds, the capabilities of the spacecraft, and the ambitions of the mission. The solar system is not a map with fixed distances printed between labeled dots. It is a living, moving system where every world traces its own path around a star at its own speed, where the distance between any 2 points changes every day, and where reaching another world requires not brute force, but patience, precision, and a deep understanding of the orbital mechanics that govern everything in motion around the Sun. Every mission we have discussed tonight, from Mariner 2's 3.5-month sprint, to Venus in 1962, to Voyager 2's 12-year odyssey, to Neptune in 1989, was designed by human beings who understood these principles. They calculated trajectories years in advance. They predicted where planets would be with extraordinary accuracy. They threaded spacecraft through gravity assist flybys, timed to the second. They trusted their mathematics, their engineering, and their understanding of the laws of physics. And they sent machines on journeys of millions and billions of kilometers through the silent emptiness of space. And in every case, those machines arrived exactly where they were supposed to be, at exactly the right time, because the universe follows rules. The planets move on predictable paths. Gravity pulls with predictable force. Light travels at a constant speed. The laws of physics do not change from one side of the solar system to the other. The same equations that describe a ball thrown across a room describe a spacecraft coasting from Earth to Neptune across 5 billion kilometers. The scale is different, the numbers are vastly larger, the stakes are incomparably higher, but the physics is the same. And that is perhaps the most profound thing about interplanetary travel. It works not because we have conquered the solar system, but because we have understood it. We cannot change the distances. We cannot speed up light. We cannot make the planets hold still. But we can calculate their motions, predict their positions, and design trajectories that thread through the clockwork of moving worlds with breathtaking precision. The next time someone asks you how long it takes to reach Mars or Jupiter or any other world, you now know the real answer. It depends. It depends on where the planets are, on how the spacecraft travels, on whether the mission flies past, orbits, or lands, on what gravity assists are available, and on the type of engine pushing the vehicle through space. There is no single number. There is only the dance of planets around a star, the physics of orbits and energy, and the extraordinary human ability to navigate a solar system that never, for a single moment, stands still. And that is something worth marveling at. We are a species confined for now to one small rocky planet orbiting an ordinary star. We have no warp drives. We have no shortcuts through the fabric of space. We have only physics, mathematics, and the stubborn human refusal to accept that something is beyond our reach, simply because it is far away. Every mission we have discussed tonight was built by people who understood that the solar system would not come to them. They had to go to it, on its terms, at its pace, following the curved paths that gravity and orbital mechanics demand. They accepted the years of waiting, the months of silent coasting, the terrifying minutes of arrival when everything had to work perfectly with no possibility of real-time intervention from Earth. They sent machines across billions of kilometers, and those machines arrived every single time because the people who built them understood the rules of a universe that does not make exceptions. The planets will keep moving. The launch windows will keep opening and closing. The distances will remain vast. But so will human ingenuity. And as long as we keep looking up, keep calculating, keep building, and keep launching, the solar system, however large it is, will never be entirely beyond our reach.